Hi, I'm Félix Nadon from the University of Ottawa, presenting our recent work toward the general framework for 3D deformable object grasping and manipulation. We'll start with an introduction to the problem and some of our current results, followed by the limitations that we observe in the current state of the art. We'll finish with the framework that we propose to address these limitations and the key challenges that remain to overcome. There are many tasks, for instance in agriculture, food processing, or medicine, that are delicate or labor-intensive because they require the dexterous handling of non-rigid objects. However, they're currently difficult to automate because robots can't match the human skills and flexibility, especially when dealing with the variance in object shape and rigidity, or when there's a mixture of objects. This is especially difficult when we have unknown objects and 3D objects. Two of the topics we've been researching for this are deformation tracking and modeling and grasp selection. At the top, we have different versions of a growing neural gas network that tracks the deformation of an object as it's being squeezed by the 3 fingers of a robotic hand here. At the bottom, the robot selected the 3 finger paths to deform the object to match or attempt to match the target contour in gold. Some of the difficulties we've noticed in the current state of the art include obtaining complete and accurate descriptions of the object in 3D. For instance, up here, if we have a complex deformable object, a single view of color and depth is not enough to fully plan the deformation. So control algorithms being developed are usually task-specific, so it's difficult to deal with a mixture of objects that have different rigidities, unknown parameters, or inhomogeneous materials. There's also a lack of large-scale datasets that involve non-rigid objects, which makes it difficult to apply many learning approaches. The framework that we propose to address some of these limitations is divided in 3 main steps, namely initialization, planning, and execution. In the initialization step, we use mainly data from an image acquisition module to identify the workspace, position of the robot, of the object, and of any obstacles that need avoided. This is information that's needed to actually define the task that's going to be performed. In the planning phase, we use any prior knowledge we have of the hand, robot, and of the object to plan the grasp and robot pose and trajectory that will allow to complete the task. In the execution phase, we use visual and tactile object tracking to make initial contact with the object and then actually run the manipulation task. In parallel with the manipulation task, we have a quality assurance module that's responsible for avoiding slippage, maintaining object integrity, and generally ensuring the success of the manipulation. When these modules are integrated, the goal is that the quality assurance module will update the object module with the true behavior of the object, which may trigger a new planning round if there's too much of a difference between the actual and expected behavior of the object. This should allow to handle objects that are initially unknown or that have uncertain parameters. Some of the key challenges that remain for implementing this framework include multi-view and multimodal sensing for detecting and tracking deformable objects. On the right, for instance, we have a large setup for tracking the motions of a pianist. It requires a lot of calibration and may not be practical for robotic manipulation in a flexible environment. There's also a need for fast and adaptable models that can accurately predict the behavior of deformable objects and be able to handle unknown objects. And to develop the quality assurance modules, we also need algorithms that are able to detect and prevent the slippage of deformable objects and to deal with unexpected behaviors. To conclude, we notice that the successful manipulation of deformable objects requires either complete prior knowledge of the object and environment to perform simulation, or highly intelligent systems that can adapt to the unknown behavior of the object. We believe that we can balance both by combining fast and adaptable models with real-time validation and quality assurance models. However, there are still many integration challenges that must be solved to get there. Thanks for watching, and feel free to send us an email with any questions, comments, or suggestions that you may have regarding this research.